All right. Good morning, AP Computer Science A. This is period A2. This is Tuesday, May 19th. Hopefully you're having a great day, and hopefully it's about to get even better with some AP Computer Science A. We have triumphed over the AP exam, hopefully. We've passed it. We've taken it. It is a thing that happened. Hopefully it went well. I just, before we started recording, I got some feedback from you on the AP exam, and it seemed like mostly positive. A couple things about timing, a couple things about uh, the questions being similar to what we practiced and some parts being different. If you have any particular questions about the AP exam, I cannot talk about the specific questions on the AP exam, like specific details about them, because number one, I don't know what they actually were, but number two, because we cannot actually publicly talk about that until the AP scores get released in July or August. So we can't actually talk specifics about the questions, but just getting general feedback, it seemed like people were pretty well prepared, so I'm happy to hear that. And I hope you did well. You should get your scores again by the end of July, early August is typically when they come out, so should be around that same time frame. All right. There is, in case you were having any technical issues with the AP exam, there is a makeup exam period. I believe it's in June. I'll have to get that exact date for you. But if you're interested in that makeup exam period, let me know, and I'll be happy to try to get that information to you. Okay, but that does exist, the makeup exam period. If you did not take the exam, you decided not to take it, or you weren't going to take it from the start, you were just like, I'm not doing it. If you registered for it and did not take it, you will receive a refund. I don't know when that refund will be processed, but according to the College Board, you will get one. And if you never paid, then there's no money to refund, so you're A-OK. Keep in mind that our URI dual enrollment for people that are involved in that is still a thing, and that is still going to be processed successfully. And as long as your grades are, in an adequate area, you should be A-OK. And by that, I mean as long as you pass, which I believe everybody here is, so that's good. All right, anyway, today, what I would like to start by showing you, and I know that you guys have the final project to work on. I know that that's a big commitment. I know it's due in just under 2 weeks, so there's a lot to do. I understand that. Um, I do, however, want to show you the last unit that we were supposed to discuss in AP Computer Science A, because I feel like it would be a disservice of me not to do that, because you're expected to have been exposed to this coming out of this class, and I feel like it is something that you are most definitely going to encounter. Not that I feel like it is most definitely something that you are going to encounter in college if you decide to pursue an AP Computer Science or an AP Computer Science major, just in this class in particular. No, a computer science major, you will definitely encounter searching and sorting algorithms. It's a big deal. It's important. There are popular interview questions. If you go for a job or an internship, you'll probably be asked about them. I know I was when I applied for my internship back in college. So I do want to make sure I share this information with you and we talk about it. As far as a graded assignment on this is concerned, I think we will probably have one graded progress assessment type of thing on this searching and sorting algorithm practice. Um, it is something that I will probably give to you next Tuesday and have it due next Thursday. So I'll give it to you Tuesday the 26th, have you guys work on it until Thursday the 28th. It should only take like 10 minutes. It's a very quick little multiple choice thing that we do in class usually. So you should be able to, get a good grasp on that, especially since you have access to your notes. So that should be even more of a benefit for you to be able to do well on that. And then, as Ryan just asked in chat, he said, is there a due date for your final project? It is Monday, June 1st. Okay? Technically, Sunday night at 11:59 p.m., which is May 31st. But if you need to get it June 1st, that's totally fine. I'll probably actually look at them on Tuesday, June 2nd. Okay? So that's the idea. So please get that to me. If you have any questions, please feel free to let me know. Some of you have already reached out to me and want to meet and talk about things. Totally fine. I'm more than willing to do that for you. So let's actually talk about searching and sorting algorithms. What searching and sorting algorithms refer to are ways that you can, given a list of data, like an array, for example, or an array list, how you can search for, aka find, specific data that you're looking for, or sort, aka rearrange specific data so that it's in order from least to greatest, or maybe in alphabetical order, or just some order of relevance, like when you do a Google search, all those elements get arranged in an order of relevance. So how does that actually happen? And what is the most efficient way to sort things on the computer? That is a question that we will not be answering, but it is a question that we will at least scratch the surface of, as far as taking a look at some common algorithms that are used to search for and sort things, when it's beneficial to use them, when it's beneficial to not use them, and you know, different mathematical properties about them. So that's really what we're going to talk about. Now, in college, I personally started learning about this my sophomore year of college, specifically first semester of my sophomore year. That was after I already had a good background of calculus and a lot of programming practice under my belt. So the concepts that we are going to be talking about are pretty advanced. However, for our purposes in AP Computer Science A, I am going to try to bring them down to the most basic level that I can, because what would be important normally if you were taking the exam is not that you understand all of the math behind it and all of the complex notations and all of the complex ideas. It's more that you just understand what this represents, why it's important, and why it's either good or bad in specific cases. All right, so that's really what we're going to be emphasizing. But we do have to do a little bit of math. We can't get away with no math. We do have to do a little bit. Specifically, what I would like to talk to you about today is we have about 20 minutes after my whole long intro spiel and our talk before class started. So I'd like to spend about 10 minutes reviewing with you logarithms, which are fun and used in computer science a whole bunch. You may have done them in pre-calculus. We're just going to take a basic look at logarithms. Some of you already might know what they are and how they work. And then the other 10 minutes talking about something called big O notation, which I'm pretty sure that nobody knows, but you may have heard of it before. All right, so let's start with a little bit of review on logarithms. You notice we got the math layout going on right now. Okay. And I'm going to teach it exactly as I would teach it in a pre-calc class. A logarithm is essentially the inverse operation of an exponent. Okay. Logarithms are used in big O notation, which is why we need to talk about them. So a logarithm. And for anyone taking pre-calc next year, you will, or taking it in the future, you will, I'm sure, talk about these at length. A logarithm is the inverse operation of sorts. I'm going to put that sort of in quotes, of exponents. And it's essentially asking the question that exponents ask in a different way. Okay? It's the inverse operation of exponents. Maybe a little more specifically, I should say it's the inverse operation of exponential functions. That's probably I should say that. It's not just the inverse operation of, say, x squared. The inverse operation of x squared is the square root of x, defined on the positive real numbers. But in any case, it is the inverse operation of exponential functions, like 2 to the x. The inverse is log base 2 of x. But in any case, the way logarithms work is essentially like this. When you have an exponent, right, say you have a raised to the b power is equal to c. Okay? What that says is a raised to the b power is equal to c. So if I gave you a problem like this, and I said 2 to the 5th equals what? What that's asking you is 2 raised to the 5th power, meaning 2 times 2 times 2 times 2 times 2, is equal to what? And of course, your response would be 32. Okay? Logarithms kind of ask that same question, but in a different way. What a logarithm would say is it would say the log base b of c, is equal to a. Okay? Is that how it would work? The log base, my fault. Log base a of c is equal to b. Oh, jeepers. For someone who teaches pre-calc, it's not going well right now. It would be the log base A of C is equal to B. So for a problem like this, I could ask you, what is the log base 2 of 32? And what that means is that's asking you 2 raised to what power is equal to 32. Whereas up here, I asked you 2 to the 5th power is equal to what? Here I'm asking you 2 to the what power is 32? And the answer to that would be 5, because 2 to the 5th power is 32. Okie doke? So that's really what a logarithm is all about. It's about seeing this number raised to this power is equal to what? This guy in a logarithm, by the way, is referred to as a base. You may have heard me just use that word just now. So when I say this is a log base 2, that means I'm asking you 2 is the base of my exponent. And what power do I raise that to get this? Okie doke. Just taking a look at a couple of examples. What if I said, just a couple random examples, the log base 5 of 25? Okay. Can we get some answers in the chat maybe? Ooh, that would be fun. What that's asking is just saying 5 raised to what power is going to equal 25? So 5 raised to what is 25? Can we get some answers? Don't be shy. Not all at once. Participation.
I'm trying to remember how logs work. Hold on.
5 raised to what is 25? 2. Kaden, you are the man. Nice. 5 squared is 25, right? So you'd say log base 5 of 25 is 2 because 5 squared is 25. Okay, let's do another one. How about the log base 3 of 81? Asking you 3 raised to what power is equal to 81? Come on, people. Come on, AP crew. 3 raised to what power is 81?
4.
4. Very good. Very good.
Nice.
Because 3 to the 4th is 3 times 3 is 9, times 3 is 27, times 3 is 81. Excellent. How about the log base, let's do base 6 of 216? How about the log base 6 of 216? That is what? 6 raised to what power is 216?
3.
3. Very good. 6 times 6 is 36, times 6 is 216. Excellent. Now, you can certainly get a little tricky when you're dealing with log problems. Something like this, if I said the log base 7 of 1/7. What that's asking you is 7 raised to what power is equal to 1/7?
That'd be -1, right?
That's going to be the -1 power, right? Remember, when you take a negative exponent, it means to take the reciprocal, it means to flip. So 1/7 is 7 to the -1 power. So you'd say that the log base 7 of 1/7 is -1. How about the log base 5 of the square root of 5? That's another tricky one. Asking you 5 raised to what power is the square root of 5? And do you remember what power is the same as the square root? People that took Algebra 2 with me in particular. 5 raised to what power? The 1/2. Very good, Lauren. Said it in the chat. That's right. So you'd say 5, log base 5 of the square root of 5 is 1/2 because 5 raised to the 1/2 power is equal to this. All right. Does that make sense? One more. How about the log base 12 of 12? What is the log base 12 of 12? What is it?
That's 1.
1. Very good. The log base 12 of 12 is 1 because 12 raised to the first power is equal to 12. Okay, very good. Does that make sense to everybody, why that's the case? Hopefully that makes sense. Yes? All right, excellent. So that's just a little overview about log. It's really talking about exponential functions the same way. Now, how does this all tie into comp sci? Well, in math, right, if you just write a log by itself, right, you just write a regular old log of x. That is interpreted to be, in this particular case, the log base 10. Okay? In math, whenever you just see a regular old log by itself, it's often it's interpreted to be a log base 10. Not often. It is always interpreted to be a log base 10 because we count in decimal and we work in base 10 all the time. So if you see just log of 100, the log really means log base 10 of 100, which is 2 because 10 squared is 100. Okay? In computer science, however, that is not the case. Okay? When you see just regular old log, which you're going to see a lot, regular old log in computer science refers to the log base 2. And the reason why it refers to the log base 2 is because of binary. Because binary is a big deal. And everything's really measured in binary at its most basic level. And so when you just see something like the log base, just log of x in a computer science context, that refers to the log base 2. I, for purposes of being consistent and making things make sense, will always write it as log base 2. I will never just write it as log, but do understand that in a lot of references in textbooks, not a lot, all, you will see it written as just log of x. But in a computer science context, log of x refers to the log base 2 of x, okay, as opposed to the log base 10, which is what's used in math a lot. Okie doke. So that's particularly important. All right. In any case, that was just a quick little overview of log. Useful, important. It's going to come into handy when we start talking about big O notation, which I'm going to do right now. Any other question on just what a logarithm is and how it works? Okay, let's move on. Okay. Let's talk about big O. So, big O notation. Now, like I said, big O is a very complicated topic. I am not going to claim to you to be an expert on the intricacies of big O notation. However, I can certainly provide you with the basic knowledge that you need. The basic knowledge of big O notation is big O notation, it approximates the complexity of an algorithm. Okay, that's really the goal of big O notation. It is used to approximate the complexity of an algorithm. All right, so big O notation of bigger stuff is going to be a more complex algorithm involving more steps. More specifically, big O notation models which mathematical function models which mathematical function can represent the number of operations a particular algorithm requires. Okay? So when you're talking about big O notation and you say the big O of something is something else, you're saying this mathematical function approximates how complex this thing is. Okay? Big O notation is always in the context of very large data sets. Okay? Meaning that we're not typically concerned with big O of like if I have 5 things in the list and I'm trying to sort it, what's going to be the most efficient sorting algorithm? Like, who cares? It's 5 things. It's going to be micro nanoseconds, if that, of a difference to sort using a very efficient algorithm or a very inefficient algorithm. However, dealing with large data sets, we're talking millions, billions, trillions of data points. this is where big O notation really shines, and this is why it's important. Because trying to sort a trillion items in a efficient way is it's going to make a huge difference of trying to sort it in an inefficient way. It's going to save money for companies on computing power. It's going to save time. It's going to save energy, all that type of stuff. So this is why it's important to talk about this. But big O notation is used for, excuse me, very large data sets. All right. Here are some common big O notations. Common. Okay, big O's. It's like a cereal, big O's. Some common big O's that you'll see. From pretty much worst to best. The worst big O I think that exists in the world is if you said that something is order, and that's the way exactly you would read it, is order n factorial. Okay. Order n factorial is quite possibly the worst big O I think that exists. It means that it is just a horribly inefficient algorithm, meaning that if you have n items in a data set, it takes n factorial operations to be able to do them. Remember that factorial is n times n minus 1 times n minus 2 times n minus 3 all the way down to n. That is really bad. So we won't see anything that's order n factorial. But there are things that exist that are order n factorial, and sometimes those things are actually unsolvable because computers just don't have the power to be able to process something like that. Okay? A little more commonly than order n factorial, though, is you'll see order of n to the x, okay, in which x is an integer. Okay? So, for example, you'll see something like order n squared, meaning that if you have n items in a data set, it takes approximately n squared operations to be able to do that. All right, n squared isn't terrible. I mean, it's not great, but it is what it is. We can kind of deal with that. Think of if you have a million items in a data set. Order n squared means you need a million squared operations in order to accomplish it. Not fantastic. A computer can do it, but it's not fantastic. All right, so we're going to try to, we want to get our order of our operations as low as possible. Something else that you see in particular is you see something that's order of n log n. That's pretty good. That's way better than n squared. N log n means you take n and then the log base 2 of n, multiply them together. That's about the order that you need. Okay, that's pretty good. Order of just regular old n is also very good, where you could say if I have a million things in a data set, it takes a million operations to sort them or search for them. That's not bad. We can do that, right? We can handle that. It's those exponential ones that start to get really crazy and out of control. Something even better than that is we could have order of just log n, meaning that if I have 8 elements in a data set, it would take log base 2 of 8, so 3 operations to find what I'm looking for. That's nice. That's easy. Easy peasy. And even better than that is, how about just order 1? There's not many things that are order 1, but order 1 pretty much means regardless of the data set that you actually have, regardless of the data, I should say this is greater than 1. Regardless of the data set that you actually have, it's just going to take 1 operation to get it done. All right? So that's what big O notation is trying to measure. Approximately what complexity of function, what exponential function is necessary to measure how long this algorithm is going to take or how many operations this algorithm requires. Okay? Again, big O is an approximation. It's not saying exactly how many. Okay? If something, say, had a list of a million things, and you ran an algorithm that just so happened to take 1,200,000 operations to do, you would still say that something like that is order n, because that extra 200,000 in the grand scheme of things, I know that seems like a lot, but in the grand scheme of computing, that is not very many. And so that we would say that that takes approximately n operations to do. Now, if you're talking about n squared, that's when you start doing something like a million squared, where you get to a trillion. Big difference, like exponentially large difference. So we're talking about approximating how long it takes. If you have something, maybe just use smaller numbers. If you have a list of 50 items and it takes you 52 operations to sort them, I'm not going to say that that's order n plus 2. I'm going to just say it's order n. It took approximately n operations to get that done. Now, if we say it took 2,500 operations to sort a list of 50 items, then that's n squared. That's 50 squared. So that's where we start getting up into n squared. N to the third is worse. N to the fourth is even worse, and that type of stuff. Okie doke. Let me give you some like super basic examples, and then we'll call it a day for now. And we'll see how this applies to my searching and sorting algorithms. All right, coming next class. So let me ask you an example. All right. If I, for example, wanted to count the number of students in this Google Meet. Okay, suppose I wanted to just count the number of students in the Google Meet. What order of operation will that be? Well, I would go to my list of people and I'd start counting. I'd say 1, look at that, Andrew, bam, 1. Brandon, 2. Caden, 3. Darius, 4. Gabe, 5. Jack, 6. Lauren, 7. Max, 8. Molly, 9. Nick, 10. Brian, 11. Right? Do you notice that there were n of you in this classroom, and it took n counts for me to actually account for each one of you. So that would be an operation that is order n. Okay? Because it just for however many people there are, I would just have to count that many people. Right? Now, what if I said, for example, I want each of you count the number of students in the meet. Okay? Now, if I said that instead, and I said each of you now count the number of students in the Google Meet, notice that that operation is much more complex because even though individually you would all be doing the same task, it's not just one person doing the task, it is each of you doing the task, right? If there are 11 of you, we would get 11 counts of 11, or in other words, this would take order n squared. Does that make sense why that's the case and why this, I mean, just think about it. This would take more manpower. This would be longer. It would take more work to do this than it would to do this. Exponentially more work, right? This gives me, all I need to do is count to 11. Here, really, we have 11 people counting to 11 or 121 counts. Does that concept make sense, hopefully? So that's just some basic examples. All right. I suppose you could then just take it even further and say each of you count the number of students, and then for each count something else, and that's where you start getting into more and more complex types of things. But I like this little example. It's a super basic one, but I think it really helps illustrate the difference in complexities. Just counting the number of students, that's just order n, right? Having everybody count the number of students, that's order n squared. All right. What if I said one more? How about just count the first student in the list? If just I'm doing that, that is something that's order 1, right? That doesn't matter how many students are in the list. If I'm just asking you to count how many students are in the list, or just count the first student, rather, bam, I would look up there. I'd see Andrew is alphabetically the first one by first name. So that would be an order 1 operation. Doesn't matter if it's 100 students in the list. I just look at the top one, bam, done. Okay, that's order 1. If I then said, how about each of you count the first student, right? Even though now all of you are doing an operation, that is 1 count, correct? So however many students there are in this Google Meet, that's how many counts there are going to be. That would be something that's order n. All right? Does that make sense to everybody, what we're kind of talking about as far as big O? It is a complex topic to talk about in detail. It is not within the scope of this class to talk about it in detail. It's just to give you the basic idea of what big O notation is referring to. It's for large data sets. It's just talking about what mathematical function represents how complex this particular task is. All right. Obviously, if you can accomplish the same goal with something that has fewer steps, then that's good. We want to try to aim for lower and lower complexities. Unfortunately, in the world of computer science, there are some things that you just can't do any more efficiently, at least not with our current technology, than a certain order of operation. Okay. Anyway, that's all I have for you guys today. Hopefully that made sense, our little discussion about big O notation. If you have any questions, please feel free to let me know. On Thursday, we don't see each other Thursday. On Friday is our next Blue Day together. On Friday, I do want to spend that time actually showcasing some searching and sorting algorithms to you, and then talking about the orders in which they operate. Okay? That's all I have for now. Logarithms will come in handy next class. Thank you so much for your attention and focus, and I hope you have a fantastic rest of your Tuesday.
See you,
Bye,
Mr.
everyone.
Giorgio.
Yep.
See ya.
Giorgio.
How about you?